Thank you. Yes, my name is Paul Jones. I'm here to talk about our startup, Machinemax, which works in the construction industry. So I'm going to start off talking about our business case. So we work in the field of construction. So you can see up here a typical construction site, a whole load of huge construction machines for digging earth, moving it around, putting it in different places. And these machines are enormous, right? So I was on site on Tuesday this week, and there was an excavator the size of a house that could dig out the amount of soil that was equivalent to the volume of this stage and dump it somewhere else as easily as I pick up this sensor. Typically, a big construction company will have a fleet of such machines, and they're very high value. These things will be worth perhaps £500,000 to £1 million. But the guys in this industry have a problem, because if they have a huge amount of machines, they don't actually know an awful lot about what they're doing throughout the day. So the operators come, and they pick up the machines, and they drive off into the site, and they don't really know too much until the end of the week, where they realize how much output they've produced. So the problem with this lack of ability to track what's going on with the machines is it encourages some bad behaviors. So the people who run the machines don't run them in the best way that they can. So one of the problems that this introduces is that when they're using the machines and they want to take a break, they won't switch the machines off. So what happens there is the machine idles, so the engine keeps running, but no actual useful work is being done. And that is incredibly costly in terms of fuel. So on the site I was on Tuesday, they had 100 of these machines, and their annual usage of diesel was 9 million liters of diesel. And if a lot of that is being wasted when the machines aren't actually doing anything useful, that is a huge problem for them, an expensive problem. So that's where Machinemax comes in, and we've developed a LoRaWan telematics solution, which we use the term a Fitbit for fat machines. So machines are not doing the best they can. We provide insight to the people who own these machines to try and improve that. So here's the architecture of our system. It starts off with our sensor, which is here. And how you would install it is you would scan the QR code, and then you go over to your construction machine. I'm going to use the radiator as an example, and you just stick it on, and that's done. So that now picks up the vibrations of the construction machine, and you can mount them on all of the machines on your site, and then you place a LoRa gateway somewhere in the site. That picks up the vibration information, and it's passed back via the cloud service provider into our back end. So the back end will store the raw packets, and then we'll run our data science engine on that. So the data science will turn that vibration information into what the construction machine was doing. Was it actively working? Was it idle, wasting fuel? Or was it off? It will store that in the machine activity database, and then the user can log in at any time via a laptop or a mobile and see what the machine's been doing. So let's have a look at what the view the customer gets. So you can see a nice, simple view here. So blue is the activity of the machine when it's on, red is when it's been idling, and gray is when it's been off. So as an operator, you can come and look at this, and you can see how much red have I got, and that's obviously bad news, and you're trying to get this number down, the total amount of idle hours. We have a web view, and then also a mobile view. So I'm going to talk about some of the design challenges we've had to create this system. Obviously, there are far more than these, but I thought I'd distill it down into some that I could cover in the time that I had. So the three I'm going to look at are battery lifetime. So ours is a battery-powered device. That's why it makes it so easy to install. How we choose which gateways we need, how many gateways we need, and where to place them, and packet loss. So hopefully these are things which other people are also interested in. So let's talk first about battery lifetime. Obviously, it's important for anyone who makes a battery-powered product. The longer the lifetime, the more value you can generate from it. And solving the problem of battery lifetime is a combination of efforts across hardware, embedded software, and system. So if we talk first about, If we talk first about the hardware, you need to select components that use the lowest amount of power possible, have low power modes, and low amounts of current draw when they're off. You need to have the ability to switch off the parts of the system that you're not using to, again, cut down on your power usage. Now, if we move into the embedded software, we need to write the code for our embedded software to minimize the amount of time when we are outside the low power mode, so keep it in low power as much as possible. We need to power on our sensors only for the minimum amount of time that we need them. There's no point having a sensor powered on if we don't need that information from it. And we need some ability to assess the impact of software changes. So let's say we make some changes to the firmware for our product. We need a way of deciding whether that's improved matters or whether it's made them worse. And then from the system perspective, we can also make decisions which either improve or reduce battery usage. So we can choose how frequently we get information from our sensor, and we can choose when we might bring it out of its low power state. So for instance, in construction, the sites maybe won't be operating 24 hours a day, so there's no use pulling information from the sensors when there's nothing happening on the site. So here is a graph of the current that our sensor draws against time. So I think the company that make this product are actually here demoing today. This is called OTII. I think it's an ARC device that they produce. And what I'm showing here are 3 different modes that our device operates in. So you can see at the bottom here, the baseline is our sleep mode. So this is the sensor in its lowest power state. So the processor goes down into deep sleep, and the current draw is very low. Then we can see these spikes that go along, and the spikes are sample acquisitions from the sensor. So the sensor wakes up, grabs a sample, stores it, and goes back to sleep. Once it's got a sufficient amount of data to justify sending a packet out, it does the bit at the end, which is a LoRa transmission. And if we zoom in on that section now, we can see this. So this shows you, if you work in LoRa, you'll spot this. This is the huge peak for the transmission. So when we launch our packet out over the radio waves, we consume a large amount of current. And then we have to be awake for the RX1 window and RX2 window for LoRa. So let's look at those 3 modes now. So we said sleep, we said sample acquisition, and we said LoRa transmit. If you actually look at the time we spend in each of those modes, we spend 98% of our time in sleep mode. That's obviously really good for battery. We spend 1% of our time each for the sensor sample acquisition, in this case 15 samples, and the LoRa transmit and potentially receive. But now we look at the average current draw in each of those modes. In the sleep mode, we're only drawing 6 microamps. And now let's compare that to the other 2 modes, where we're right up into the milliamp range. So actually, we're drawing more than 1,000 times the amount of current in these modes than we do in the sleep mode. And that just goes to show how really important it is to keep the amount of time you spend asleep the maximum possible. And then if we look here at the power consumption, the contribution to the power consumption is 1% from this mode, even though we spend 98% of the time there. And the bulk of the power consumption is in these 2. So let's move on to the next challenge, gateway placement. So how many gateways do we need to cover a site, and where should we position them? And that's in the ideal case. And then also, what constraints are there on the placement? So when we get a potential customer, we will first look at online maps to determine the size and shape of the site, and the potential locations for power, which will be where the site office is based. Typically, sites have no internet connection we can use, so we're forced to use a 3G or 4G backhaul. Then we'll make a site visit, which will give us some idea of the topology of the site, so we can then see, are there hills, are there drops, and we can identify some specific gateway locations. Some may be out of bounds due to health and safety, and we can use a sensor in a mode of GPS ping to map out the area. So here's an example of data from one such mapping. So we have a sensor which is getting a GPS ping and reporting it back over LoRa to the gateway, and we can see a cluster of points which tell us what locations we get good signal and what locations we don't. So let's look at some potential issues we might get on site. So one problem is obvious, the site size. So this is a huge site, 4 kilometers from the site office to the edge, so 8 kilometers end to end. So we're probably going to have multiple gateways to cover that. Another potential issue is building obstruction. So this is a construction site where they're building housing development, and the buildings, as they go up, are going to create more and more obstructions. And then the third issue is topology. So this is a quarrying site. So actually, you can't see it very well, but they will dig down into the ground, removing material. And that, again, causes a problem, which we'll see here. So as you dig down into the ground, your construction machines are in a hole. And so you can't get connectivity from a cell tower. If you go down into this site, you'll have no mobile phone reception. But LoRaWan can help with that. So it can extend the network range by, if you put a gateway on the edge of the site, you can talk via LoRa for a short while and then do the 4G backhaul to the cell tower. And now into our third design problem, which is data loss. So we have two kind of types of data loss. We have RF contention, where perhaps two devices transmit at the same time on the same channel with the same spreading factor, and they interfere with each other. And what that typically manifests itself as is a single packet loss. If you're looking at my earlier slide, you may have noticed that, a white gap. Nicola was talking about this in his keynote earlier today, and he said the solution is coming for LoRaWan using forward error correction. Now we look at our second type of data loss, and this is out of range. So a construction machine drives away from the gateway so far that it can't communicate anymore, and what happens is we end up with large chunks of data being missed. So this is a much bigger problem. And that problem can't be solved with forward error correction, so we have to use a different solution. And in this instance, what we'll do is every message that we will transmit, and we will still be transmitting because the device itself doesn't know that it's gone out of range, every device we transmit, we will store in flash memory. And then we'll wait until the construction machine goes back into sight, back in range, and then we will intersperse our normal data packets with additional data packets which are retransmitting the data that was missed. And that's all triggered by a downlink message from our back-end server. So that's the end of my talk. Are there any questions?
Any questions? Yeah, we have one here.
Hi, thanks. That was really interesting. I'm just wondering, is it vibration data only that you're gathering, or is it location, or what data are you sending back?
So I can't hear very well. Could you?
Oh, sorry. I'll just say that again. I'm just wondering, are you recording and sending location data, or is it just vibration data?
Yeah, OK. So we do have a GPS sensor on board our device, and we can get GPS data back. The problem is that GPS uses an enormous amount of battery compared to the other type of sensors that we use. So we can't send GPS information constantly because it would drain our battery so fast. So what we have to compensate for that is you can send a downlink message which says, I want to know your location. We'll grab a GPS ping, and we'll send that back over LoRa. So we can't produce, for instance, a real-time map of where you've been, but we can say, on this day, you're in that location.
And with that, I think I'm going to... You find them afterwards, because we have 15 minutes for 2 speakers left. So I would like to have a warm applause for Paul Jones.
Thank you.
Well done.